Hello everyone, I am Pritesh Srivastav from TFR Mumbai. I am working with Professor Bahadur Singh. So today I will be talking about my work on realizing spin valley polarized nodal fermions in RBV2T2 class of altermagnets. So traditionally we know that and there has been a lot of talks on it that this valley apart from spin and charge can also act as a degree of freedom, and if we have a way to polarize these valleys have a opposite polarization, then we can realize interesting phenomena such as valley Hall effect and so on. One such case is in inversion broken AB2 type TMDs, where the K and K prime valleys have opposite spin splitting, and yeah, they give rise to such effects. Now we are asking that question that can we have a non-relativistic way of polarizing the valleys with opposite spin, and which is generally stronger than the SOC effects. Also, can there be some topological phenomena which is spin valley polarized? So we propose RBV2TE2 class of materials as a novel route to for realizing this topological valleytronics. So very briefly, altermagnets are system where the magnetic atoms are like the magnetic moment of atoms is like that in antiferromagnets. However, the non-magnetic atoms form this anisotropic sublattice around that magnetic atom, which are related by rotation symmetry or mirror symmetry. This leads to spin split Fermi surfaces. Now, how the Fermi surfaces are spin split depends on what the real space symmetries are. So, suppose if we take a tetragonal system and we want to polarize the two x1 x2 valleys in opposite with opposite spins, we want the system to have diagonal mirrors instead of axial mirrors. In that way, we can make the valleys spin polarized. Now, the RBV2T2O are experimentally realized altermagnets where the vanadium V2T2O form a quasi 2D structure, and the rubidium or other alkali elements are intercalated in between these lattices. RBV2T2 falls in space group 123, and it has this diagonal mirrors which gives it okay, somehow this is not appearing, but it makes the Brillouin zone spin split. And it's also seen in this local magnetization density around the V atoms, which is related by this fourfold rotation symmetry. Now, if you look at its electronic dispersion, so we can see that in this M gamma Z A direction, the bands are spin degenerate. However, the bands are spin split in all directions, although the total density of states is equal for up and down spin bands. If we look around the X valley, we see multiple band crossings around it. If we particularly look into these three bands, so firstly, if we look at around the X1 valley, we have a nodal line formed by the upspin and downspin bands at the X1 and X2 valleys. These nodal crossings are formed by opposite spin polarized bands, so we call them spinless nodal crossings, and they have a type 1 dispersion. If we also see that there are also nodal crossings formed between the same spin bands, which basically make the two valleys spin polarized. So X1 valley and X2 valley have this nodal fermions which are having opposite spin, and this we characterize it as SP1. Now, there are also type 2 nodal lines formed between opposite spin bands just near the Fermi level, which we are calling as SL2. Now, type 2 nodal lines are special in their own way because they violate the Lorentz symmetry. Their dispersion relation essentially violates that. So, in essence, we have multiple nodal fermions polarized about this X valley in this system. Now, the question is, if we see it in throughout the Brillouin zone, we can see that all these nodal lines basically are centered about this x1 point, this spinless and spin polarized nodal lines, which are making it spin valley polarized. Now, the question is whether they are topologically robust or not. So we can see, we can actually calculate the MZ mirror eigenvalues. We found out that the SL2 and SP1 nodal lines are composed of bands with opposite mirror eigenvalues, which makes them topologically robust, and they also have a non-trivial Berry phase pi. For SL1, they are composed of bands with same mirror eigenvalues. That's why with effects such as SOC, they basically gap out. So, so we have this spin polarized SP1 nodal lines. Now, yeah. So now the question is, we have multiple features just near the Fermi level. Can we isolate this spin polarized nodal lines near the Fermi level, and so that we can obtain a topological feature which is spin valley polarized? So there are multiple ways we can actually tune the system and try to tune its topology, and each leads to a lot of different effects. I'll today focus on how we can use this to drive, yeah, how we can use this to drive the spin valley, spin valley polarized nodal line closer to the Fermi level. Now, firstly, to understand this, how can we obtain this spin valley polarized model? We constructed a minimal model to understand the system. So we constructed a basis based depending on the xz and xy orbitals which are constituting those three bands, and we realized that the reason for the appearance of this spin valley polarized crossing is the anisotropy between the xy and the xz orbital. Like these both have opposite nature, which results in their opposite spin splitting, which results in the spin valley polarized nodal fermions. So to understand this, we have this phase diagram where lambda is the effective anisotropy parameter, and we see that as we tune lambda towards higher and higher values, we go from a spinless nodal line near the Fermi level to spin valley polarized nodal line at the Fermi level, with these basically bands going far ahead and gapping out. Now, how can we actually realize in the real systems? One of the ways is to go from the bulk limit to the monolayer limit. As we went to the monolayer limit, naturally the anisotropy between the xy and the xz orbitals increased, and which naturally results in this spin valley polarized nodal lines at the Fermi level. This was for V2TE2O, where these atoms are absent, RB atoms are absent. If we instead take RB atoms, RB V2TE2O monolayer, in that case the RB atom present here breaks the mirror symmetry. This results in breaking of the topological protection, where the nodal line gap out in all direction except the Brillouin zone boundary, leading to a wild semi-metal phase instead of a nodal semi-metal phase. So we are also able to obtain a topological phase transition. We were also able to, in other systems, we are also able to see valley polarized wild nodes, but this is a different system. I won't be going into detail in that. So summarizing, we were able to propose a system for topological nodal line fermions in RBV2TE2O, and we were able to tune it to make its system spin valley polarized, and we investigated different effects. How can we basically tune the different topological phases? Yeah.
Yeah. So good afternoon, everyone. So I am Shayok Bhomik from IOP Bhubaneswar, and I am going to talk about superconducting diode effect via Floquet topological full day Fedel phase in driven Rashba nanowire. And this work is recently archived and is done with my PhD supervisor, Professor Arjit Saha, and Professor Tanay Nag from BITS Hyderabad. So in last few days, we have already witnessed some exciting talks about periodically driven Floquet systems, then topological superconductivity featuring Majorana zero modes, and also the exciting superconducting diode effect, which is the manifestation of non-reciprocal charge transport in superconductors. And so right now at the very end, I take this opportunity to talk about the interplay between Floquet induced topological superconductivity and the unconventional finite momentum pairing, the full Ferrell pairing, and the non-reciprocal signatures of superconducting diode effect in a single setup. And also furthermore, I will talk about how this non-reciprocal current signatures in superconductor is linked to the switching between distinct topological modes just by changing the direction of the current. All right, so we all know this PN junction diode. So in a PN junction diode, semiconducting diode, so the reverse bias characteristic and forward bias characteristic is completely different. So there is a non-reciprocal non-reciprocity involved. And now in superconductors, so we have this critical current, the maximum current the superconductor can withstand before the breakdown of superconductivity and transiting to the normal ohmic state. So you can see, so for a diode configuration to realize in a superconductor, we have to have asymmetry between critical currents in opposite direction. So for example, this gray line, this is just a conventional superconductor, the critical current, positive critical current and negative critical current is same, so no diode effect. Here in the red line you can see the critical current, the IC plus and IC minus are not equal and opposite, so we can realize a superconducting diode effect. And it has been seen that inversion and time reversal symmetry broken superconductors exhibit this kind of features, and there has been multiple works in superconducting diode effect in various range of systems featuring multi-layer superconductors, artificial superlattice, Josephson junctions based on magic angle twisted bilayer graphene, and there is a nice review article that actually chalks out all the possible setups and materials where superconducting diode effect has been realized or it is possible to be realized. And in the context of our interest, the semiconductor superconductor hybrid structures, so it has been seen that the key ingredient that actually takes part in this process is the FFLO pairing mechanism or the full Ferrell pairing mechanism. Okay, so let's just briefly look into this. So let's say I have a two-dimensional electron in a lattice and subjected to Rashba spin orbit coupling. So we know that the Fermi surface is splitted in two concentric circles. And let's say another scenario where we have just the Zeeman splitting. There also we see the Fermi surface is splitted concentrically. So in these two cases, if I want to introduce superconductivity, it is always a BCS type pairing where the net Cooper pair momentum is 0. Now if we have both Rashba SOC and Zeeman splitting, so we can see the Fermi surface is not concentrically split, so there is a finite shift in momentum and there is a possibility of having a net center of mass, finite center of mass momentum pairing, which is the full Ferrell Larkin-Ochinokov or full Ferrell pairing if the Q value is exactly unique. Now in the mean field level we can start from an attractive Hubbard interaction, local Hubbard interaction, and we can mean field decouple it taking the S wave FF channel. This is the form of order parameter delta e to the power IQR. This Q is the Cooper pair momentum, which can be realized through externally injected supercurrent. And so this after decoupling you can see that in momentum space the pairing looks like exactly a finite momentum pairing. Its total center of mass momentum is finite. So to establish that the superconductivity is exactly full Ferrell type, one has to self-consistently obtain the ground state of the superconductivity and show that the ground state exactly arises at a finite value of Q, or the current carrying state, which is the zero current state. Yeah. So now let's talk about our work. So what we have is we have a one-dimensional Rashba nanowire in close proximity to a bulk S-wave superconductor subjected to a time-varying magnetic field in this step driving fashion, where I have this driving protocol. This H1 is just the Zeeman term and J0, H0 is just the mean field static lattice Hamiltonian. So we can write an effective one-dimensional lattice Hamiltonian, a mean field static lattice Hamiltonian. So this is the T is just the Bayer hopping and alpha is the SOC component and chemical potential mu, and we consider the superconducting term delta e to the power IQN. Now if we are interested in the stroboscopic limit, where we just see this dynamics in intervals of time period t, So we can construct this flow k operator ut, and the flow k operator is does not exhibit any time dependence, but it encodes all the information of the dynamics. So we can finally diagonalize this ut and get the eigenvalue spectrum, the flow k quasi eigenvalue spectrum. And now looking at the spectrum, so we see something interesting. So if we look at the spectrum as a function of J1, the driving parameter, we can see that if we shift the driving parameter by 2 pi, this is attributed by a pi shift in the spectrum. So in the context of topology, there is the conventional zero energy Majorana modes, and due to this driving, we can have this dynamically generated flow k pi modes, which is finite energy modes, which arises at the boundary of the flow k Brillouin zone, plus minus pi. And here we can exactly see that the energy spectrum as a function of this driving amplitude J1, we can see that at finite J1 we can have the 0 modes, and shifted by 2 pi we can have these pi modes. Now interestingly, for a current carrying state which is realized for a finite value of q, you can see that if we change the sign of q, that is also attributed by a change in pi, energy pi. So that means this the system selectively realizes topological 0 modes and pi modes in different q sectors, which is realized by supercurrent, externally injected supercurrent. So what we are trying to say, in the interest of time, I think I have to finish. So what we are trying to say is that if we see the eigenvalue spectrum as a function of q, the positive q sector, which is attributed by negative supercurrent, that only realizes 0 modes, and the negative q sector, which is attributed by positive supercurrent, that realizes pi modes, and these are non-reciprocal. So the non-reciprocity is also interlinked with the topological signatures. Now this is a self-consistent analysis. So we validate all the results that we are showing over here. So this is the last slide. I'll just wrap it. So in the self-consistent result, so what we are doing is that we self-consistently solve the superconducting order parameter, and we plot the energy eigenvalue spectrum utilizing the self-consistent solution of order parameter, as parallelly we also plot the current. So in the scenario 1, we can see that the positive current leads to topological transition for only exhibiting pi modes. However, the 0 current or 0 q state does not have any topological signature. In the second scenario, you can see the negative current, this side we have for a finite negative current we have topological 0 modes. And in the third case, the most interesting case, you can see that by tuning the direction of the current, you can go from topological 0 mode to a topological pi mode. And since the current is a bulk quantity and topological features are edge effects, boundary effects, so you can see that this current is also having a signature of the topology, bulk boundary signature. So when entering the pi mode, you can see a sudden shift in the slope, and entering the 0 mode, you can see there is a finite jump in the current. And this can be understood by the profile of the superconducting order parameter at 0 temperatures. You can see that this particular regime specifically, you can see the superconducting order parameter itself has a suppression, and the suppression is almost smoother when the temperature is high. So in summary, if I conclude, so what we are showing is that we can have a supercurrent induced topological transition, and this supercurrent induced topological transition is also linked to the non-reciprocal switching of topological 0 and pi modes. And you can see that not only the supercurrents are asymmetric, the critical currents, the maxima and minima of the currents are also asymmetric. That means we can have a diode effect, and this is the efficiency which quantifies the diode effect, and we can see that we have a maximum 45% efficiency if we optimize biochemical potential and driving strength self-consistently. All right, so thank you.
Very nice. So we can actually ask one two questions. It seems not. So let's thanks Sayed.
Okay, so good afternoon everyone. So I'm Amar Verma from UMDA Center for Excellence in Basic Sciences, and I'm working with Dr. Sangeeta Bose. and today I'm going to present about disorder-driven quantum phase transition in nanoporous ambient thin film. So, quantum phase transition has been already studied in many years, and it do not need any introduction. Still, I'll just try to briefly introduce it. So, we all know that classical phase transition happens because of the thermal fluctuation present in the system. But what happens at the temperature 0 Kelvin when there is no thermal energy left? So, at this temperature, another type of phase transition happens that is known as quantum phase transition. So, this quantum phase transition is governed by the quantum fluctuation, and it is tuned by the non-thermal control parameters such as disorder, magnetic field, and carrier density. So, this is the phase diagram that explaining that phase transition, and here we can see QCP, which is a quantum critical point at which the transition is happening. So, this transition has been already studied in many systems. So, the most exciting system is the superconductor system, where it had been studied extensively, and this is why, because the tuning of external parameter is so called easy in this kind of system. So, why quantum phase transition is, how quantum phase transition is studied in superconductors? So, it is studied in the form of SIT, superconductor to insulator transition. So, here are some examples present. So, the first one is the amorphous bismuth film, where we can see the transition is happening from superconductor to insulating with the reduction of the film thickness. The second example is of MOG, where the transition is happening from superconductor to metallic transition. So, this is happening because of the because of varying of magnetic field. And the last one is the unconventional superconductor, that is monolayer BISCO. So, here the transition is happening because of the decrement of the concentration of oxygen. So, this transition is happening like from superconductor to insulator. Another example is of NBN. So, since I am working on NBN, recently on NBN also such kind of phase transition had been seen, and this is seen by going to very extreme low disorder, low thickness. So, why this is so important? So, what are the scenario for superconductor to insulator transition? So, we all know that superconductor has a complex order parameter which has an amplitude and a phase. So, here the one has to note that the phase gives rise to another energy scale, which is superficial stiffness, which is the energy required to twist the phase of the condensate. So, here the amplitude and phase, there are many debates going on which are saying that which is responsible for such kind of transition, like bosonic mechanism or the fermionic mechanism, and also what is the origin of such kind of intermediate metallic state which are present in some kind of SITs. So, most of the study has been done on the plane system, planar pristine system, but what happens when we use nanoporous geometry? That means a superconductor system which has a nanopores present inside that. So, we are working on such kind of system. So, here we have seen that the second energy scale, that is superficial stiffness, decrease substantially in the case of nanoporous film. So, here we can see for the 15 nanometer film and 5 nanometer film, and for the 5 nanometer film the GS decreases from around 240 to around 12. So, not only this, we have also observed Berinsky-Kostelis-Thoros phase transition in such kind of nanoporous film. So, this is a result for a 5 nanometer film, where we see that for the 5 nanometer pristine system we do not see a sharp BKT, but for the case of 5 nanometer nanopore on the nanoporous system we see sharp BKT phase transition. And also it tells that our system is going towards showing a 2D nature. This work has been published recently in PRB letters. So, if anyone is interested, they can see this article. So, here we can say that the nanoporous geometry can significantly influence the quantum phase transition. Also, previous results, some studies have shown that the nanoporous amorphous bismuth film with is shown already such kind of SIT by varying the film thickness. So, this is already being studied in some kind of system. So, we are trying to study in this NBN. So, how we are making our films? So, we are making our films on the nanoporous anodic aluminum oxide membrane, which are a template which are having such kind of nanopores, and we are growing our film on these substrate by DC magnetic sputtering. What we are using, the template that we are using has shown a different interesting surface morphology. So, here we can see that these two morphology, the bottom and the top surfaces are having different morphology, and when we grew a film on these substrates, what we observed that one of the film is showing granular behavior, where the another film is a continuous behavior. When we did the transport measurement of these films, we observed that the continuous film of the 10 nanometer film is showing a TC around 10.5, where the bottom surface, that is D1, is 8.5, where the top surface, where the D2 is 4.5. That means with the same morphology we are able to tune the disorder for the same thickness. So we have studied the sheet resistance of this film, and we observed that the D2, that is the more disordered film, is having a 6-fold increase in the sheet resistance for the 10 nanometer film. We wanted to quantify the disorder, so that we studied the Hall measurement, and we all know that the KFL, the IFL wriggle parameter, shows the measurement of the disorder. So here we did for the 5 nanometer film, and we observed that the KFL is decreasing from 3.75 to 1.08 for the 5 nanometer film. That means we are able to. Yes, sir. Yes, sir. I'll just go to the result part. So here we can see that we have grown different films of different nanometers on both the surface, and we have shown such kind of SIT, and we have seen that for the 6 nanometer D1 we can see as a superconductor, but for different thicknesses we observe intermediate metallic state also, where the resistance is saturating at lowest temperature. We have also seen such kind of insulating states also in our different films. So we have also plotted the Arrhenius plot, where we have seen that for metallic state we have seen the saturation of the metallic films. So still the key question is still there, that is what is the governing factor for such kind of SIT, bosonic or fermionic. So to address this question, what we have studied is vortex matching effect, which is nothing but, so when the superconducting film with the periodic nanopores are placed in magnetic field parallel to the axis of the cylindrical hole, they exhibit periodic oscillation in their superconducting properties, like critical current or magnetoresistance. So here are some example where we can see a resistance oscillation. The magnetic field at which the oscillation is present is called as a matching field. This is the formula for the matching field, and the where phi naught is the superconducting flux quantum. So whenever we see such kind of oscillation at such a magnetic field, we can see there are Cooper planes present in the system. So this is the main result that this is the origin of the matching effect, which I will not discuss here. So this is the main result that I want to discuss. So for the superconducting film, we have seen such kind of oscillation in the film with 4 matching field, and we can see the resistance is very low. For the metallic film also we can see such kind of oscillation. The resistance is increasing as we increase the temperature, and we can see that the resistance is saturating around 30 ohm, but still we can see vortex matching effect. As we go towards the next metallic state, that the 4 nanometer D1, here also the resistance is saturating at 200 ohms, but still we can see such kind of oscillation. That means vortex matching effect. Just a second, it is just finished. And the next stage is the insulating regime. So in the insulating regime also we have done such kind of measurement, and we have seen such a vortex matching effect. So that means in the insulating regime also we are able to see such kind of oscillation, and there are localized Cooper pair. But as we increase the disorder more, we are not being able to see such kind of oscillation. That means after certain disorder level, the Cooper pairs vanishes. So this is the main result that I want to share with you all. This is the conclusion, and I would like to thank my guide, RIE, for the funding, and my lab mates. Thank you so much.
Questions? It seems not. So again, let's thank.
Thank you.
Right?